So, today we will discuss about some basic components in optics lab. So, if you go to optics lab for doing experiment, so what are the common uh, components, basic components you will use in optics lab. Uh, so these components are basically, you can tell this mirrors, then lenses, then prism, then you can say grating, gratings, then spectrometer, then light source, also you need spirit level, then you need the uh, knowledge of using uh, vernier calipers or slide calipers. So, etc., etc. There are many components. So, today these are basically uh, if you have this class 2 class 12 knowledge, so you know most of the working principle of most of the components, but here just again I will revise that one. So, let us start with the mirror and lenses. So, mirror, you know that mirror generally is three kinds of mirror we use, basically plane mirror and uh, concave mirror, convex mirror, right. So, mirror works basically on the principle of reflection. Laws of reflection we know, and we are quite familiar with the reflection from the plane mirror. So, basically this is the plane mirror and this NO is the normal. So, AO is the incident rays, then it is reflected from the mirror, that is OB is the reflected rays, right. So, with normal this angle is, incident angle is theta I and reflected angle is theta r. Also angle one can define with the surface of the mirror. So, if that is phi I, so this angle, incident angle with the surface of the mirror, if it is phi I, and this other one reflected one, that is angle between the reflected one with the surface, so that is phi r. Okay. So, this laws of reflection tells that the angle of incidence with normal or tangent, okay. So, that tangent I have used this word, it is basically valid for the curved surface. Okay. So, uh, this angle of incidence with normal or tangent is equal to the angle of reflection with the normal or tangent. Okay. So, let us see the concave mirror. concave mirror. Okay, this is the concave mirror. So this concave mirror, it's the is the curve one. So it is a part of basically a sphere. Okay, it's a part of a sphere. So one small portion of a sphere is basically is the concave mirror. So when it is a sphere, so it has center. Okay, that's the basically C. And what is the part of the mirror you are taking? So middle of that one, it's a basically uh, pole. Okay, so this line is basically axis. So I will tell you more. So here basically I am putting emphasis on the reflection. So one ray is coming and falling at this point. Okay, now it is reflected from this point. Okay, so how it is reflected? It basically follows the laws of reflection. That means angle of incidence will be equal to the angle of reflection. So how we will find out? So basically at this point you have to draw a tangent. Now normal to the tangent is this is basically uh, is the radius of the spheres. This is the radius of the spheres. Okay, so this is the normal at this point from where this light is reflected. So here also reflection, uh, light will be reflected in such a way it will follows the laws of reflection. So this angle theta I will be equal to the theta r. Okay, so as if this part, this small portion here, it is like a plane mirror. Okay, so whatever the from plane mirror, whatever the uh, ray diagram, so here also similar ray diagram we are drawing. So as if this tangent is the plane mirror. So from this plane mirror, this it is reflected as we have seen here. Okay, so similarly at this point also same way it's reflected. So this is a tangent. Okay, here also this along this axis it's called principal axis basically. So pole and this center uh, of the sphere. So this line is basically principal axis, and if light falls along this, so you know this basically it is the normal, it's the it is the normal at this point. Okay, so light is along the normal, so it will reflect it along the normal. Okay, so here basically incident angle is 0 and reflected angle also 0. Okay, so now similarly this convex mirror also, if you see that this is the incident ray at this point. Okay, now it is reflected from this point, it is reflected. So here again you have to draw tangent. So this tangent as if this plane mirror. Now on this tangent, this is the normal. So angle of incidence with this normal will be equal to the angle of the reflection. Okay, so here also it's basically from curves. Here what I want to emphasize that the reflection from the mirror, whether it is plane mirror, whether it is curved mirror, this reflection occurs following the laws of reflection. Okay, if so, so just I can write in general way. So angle of incidence with normal or tangent will be equal to the angle of incidence with normal or tangent, right? Then second law is basically, it is generally we ignore it, but it is very important when we are going to draw it. So all the time we draw on the plane of the paper, so that's why we don't realize. But in in some when you are going to do experiment. So, there in reality, so this law, second law is very important. So, when you are going to search uh, the reflected ray in space in 3 dimension, so then in which way you will get the reflected rays. So, that you can find out, you can guess only following the second law of the reflection. So, second law of the reflection is basically incident ray, normal or tangent, and the reflected ray will be on the same plane. That means, this is the incident ray, this is the normal, or this is the normal, or this is the tangent, okay, and this is the reflected ray. Okay. So, these they will be on the same plane, okay, because according to first law, incident reflected ray will be equal to the incident ray. So, this ray, whether it will be on this plane or it will be in this direction, making the same angle with the normal, it is possible. So, it can make a cone basically, okay, with the same angle, violating, without violating the first law, it can reflect a ray can be any line, any ray on the cone with the with angle of theta r. So, this second law is fixing that in which direction you will get the reflected ray, it will be only in one direction. So, that is basically it will be this direction, because incident and the normal or tangent are on the plane, on this plane. So, reflected ray has to be on this plane. Okay. So, this action or working principle of the mirror is basically, whether it is plane mirror or curved mirror, so it is basically all the time it follows the laws of reflection. So, another important fact I will tell you, you know, but in many experiments we need this concept. What is that? This on the mirror, light is falling, okay. Say this is the source, and from source light is falling on the mirror, say falling perpendicularly. So, reflected ray also it will follow the same path, okay. So, I can put a detector here to catch the reflected rays. So, this concept is very important in particularly one experiment I know, this is the X-ray diffraction experiment. This very common experiment for characterizing structural characterization of the sample. Okay. So, there this concept is very important, and we use this concept. Okay. Although we know, but when in reality I have seen that one has to really implement this knowledge to that experiment, XRD, X-ray diffraction experiment. Okay. So, now generally in XRD experiment we change the incident angle, and catch the reflected rays. Is basically diffracted ray, Bragg diffraction. It is equivalent to reflection under some condition. Okay. So, we can say that is the Bragg reflection. So, we have to catch the reflection. Okay. So, we will vary the incident angle, and then we will catch the reflected rays, okay, using a detector. So, that is the experiment, XRD experiment. So, now how you will change the incident angle? So, very easy way generally to think that we will change the position of the, we will rotate this, we will rotate the source Okay, we will rotate the source, we will rotate the source. That means with normal it will make a angle, it will make a angle, right. So, following the laws of reflection, so it will be reflected. So, compared to this position now, the source is rotated by angle theta from the normal basically. So, reflected ray will rotate in other way, other direction. So, by theta. Okay. So, or theta I and theta r. So, these two will be same. So, if I rotate the rotate the source, that means incident ray by angle theta. So, detector will rotate the, or reflected ray will rotate by theta on the other direction. Okay. So, now generally in XRD experiment, it's this source, X-ray source is very heavy and it is very difficult to rotate the source. Okay. So, but we have to change the incident angle. So, instead of rotating the source, we rotate the mirror. We rotate the mirror. In that case, we rotate the sample. Sample surface is basically very smooth and it works like a mirror. Okay. So, if I rotate the mirror by angle theta, source is at the same position. Now, if I rotate the mirror by angle theta, so this normal to the mirror, it will rotate by theta. That means the incident angle now with the mirror will be theta, right. Now, source is at fixed position, detector also was at this position, right. Now, if I change the source, rotate the source by theta, so detector also I have to rotate by theta. But in this case, you can see that source is fixed. If I rotate the mirror by angle theta, so it will make incident. So, incident angle is basically theta. It's in this case, okay. But detector, now I have to rotate by 2 theta, okay, because here this reflected ray, so this is the angle theta. Now, this other one reflected ray will form the angle with this normal, that is also theta. Okay. So, from this position, source position, now reflected rays, or with respect to the incident ray, reflected ray is rotated by, compared to this, is rotated by 2 theta. Okay. So, although in both cases incident angle is theta, but when you will rotate the source, so detector has to rotate by theta in this case, but other case when you will rotate the mirror, and incident angle will be theta, but the detector has to rotate it by 2 theta. So, if mirror rotated by theta, that means I am changing the incident angle by theta, and detector to catch the reflected rays, we have to rotate the detector by 2 theta. So, that you know, but still I just remind you, and this is very useful for XRD experiment. This concept is required. So, just I emphasized. Okay. So, so in case of mirror, so let us discuss about the convex mirror and concave mirror. So, that's basically they are spherical mirror. Okay. So, it is a from a sphere, it's a small portion of the sphere is taken. Okay. So, this the mirror, generally we just draw this part, we just draw this part. Okay. But it is a spherical part of a sphere. So, this aperture of this mirror, basically the radius, the diameter of this of the diameter, not diameter of the mirror, diameter of the basically periphery of the mirror. Okay. So, these basically circular, this when you are taking this spherical part. So, this is a circular part. So, diameter of the circular, that part is basically is called the aperture. So, in this case m dash is the aperture, this is the diameter of the upper surface of the this or edge this of the mirror. So, that basically aperture we use, this is the basically in terms of the incident rays. So, this size, this aperture tells this what is the space on the mirror to enter the incident light. Okay. So, so here nomenclature is this basically this is the concave mirror and this is the convex mirror. Okay. So, this is the middle of this center of this mirror. Okay, is called pole, and the C is basically the radius of the or center of the curvature, if the center of the curvature C. Okay. Or basically is the part of a sphere, is the part of a sphere. So, this is the center of the sphere, this is the center of the sphere, right. And so, this CP, basically this line passing through the CP, that is the called principal axis, that is the called principal axis, right. And if you draw the reflection from these mirrors. Okay. So, then you will see the reflected rays, they will form the basically image. Okay. So, actually for getting the image, we have to draw the ray diagram. So, there are rules for that. Okay. Everything will happen due to the reflection, as I told you, discussed you, but all the time seeing this reflection, measuring the angle, it's not the easy way. Okay. So, if you follow some rules, then it is easy to draw the ray diagram. So, here this three special rays, one ray say parallel to the principal axis, incident ray parallel to the principal axis, incident ray parallel to the principal axis. Okay. So, this reflected one, it will pass through a point F, it is called the focal point. Okay. So, this is one rule we will follow for drawing the ray diagram. Second, this passing through F, incident ray, if incident ray passing through F, then reflected incident ray passing through F, then incident reflected ray will be parallel to the principal axis, parallel to the principal axis, reflected one, okay, parallel to the principal axis. So this is basically parallel to the principal axis. Third one is, if rays, incident rays passing through C, incident ray passing through C and falling on the mirror, then it will be reflected along the same path, it will be reflected along the same path. So this whatever three special rays, whatever I told you, so that basically this it follows the laws of reflection, right. So so this is basically is the this ray is, it will fall on this here, basically is the perpendicularly, okay. So that is why it will return back, okay. So other case also this same way one can explain from the basic laws of reflection. So this whatever special ray, whatever I told you, this is valid for this convex mirror also, right. But in this case basically it is reflected as if, so if you just extend in the back side of the mirror, extend the back side of the mirror, so they will meet some point on the principal axis. So in this case here meeting this ray, whatever F directly here meeting, so that is F here extended one. So these are reflected as if this reflected ray is coming from this point, reflected ray is coming, so here this incident ray, okay, and then so as if this incident ray, the uh, source is here, okay, or it is passing through as if it is following this incident ray which is passing through this F, right. So this is the extended one here also same way. So in this case this focal point and the uh, center of curvature is on the other side of the mirror, okay, back side of the mirror, it is on the front side of the mirror, right. So 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 if you draw the ray diagram, if you draw the ray diagram for say concave mirror, say concave mirror, okay. So depending on the position of the, depending on the position of the object, depending on the position of the object, you will see the image, you will see the image of the object of at different distance and of different nature and of different size, okay. So if your object is at infinity, okay, that means parallel rays are coming and falling on the mirror, okay. So this image position will be basically at the focus, at the focal point of the mirror, and it will be real image and inverted, okay, real image and inverted, okay, and it will be very small size, point size, this image size will be point size, okay. If you put the object beyond C, means the distance is greater than Cp, okay, then this image you will get between F and C, and it will be real inverted image, and it will be smaller size than the object size, okay. So that is why we have written diminished. If you put at C, object at C, center of curvature, so you will get the image also at the center of curvature, and it will be real image and inverted one. So, this, but the size of the image will be same as the object size. So, if you put, that means you are reducing, you are decreasing the distance of the image, distance of the object uh, with respect to the mirror. Okay. So, this and size of the image we are getting, size of the image we are getting uh, larger and larger, and image, image basically it is shifting, it is shifting outwards. So, it was at focus, now it is, now image position is between focus and the center of curvature, now at the center, now beyond, not center, center of curvature, now beyond center of curvature, now at infinity. Okay. Now, it is the beyond mirror. So, if your position of the mirror, this object between F and P pole. Okay. So, object distance is less than the focal length. So, then image you will get the beyond mirror, behind the mirror basically, and you will get virtual and erect. All this case you are getting inverted, in this case you will get erect, virtual erection. Okay. And it will be enlarged. Okay. So, this the position, nature and size of the image whatever I told about the concave mirror. So, for convex mirror also you will get this same thing. Okay. So, just let me show, I tried to draw, I tried to draw it. Okay. Just let me show you. So, in this case object is basically at infinity. So, parallel rays are coming. Okay. So, they are meeting, you see, at this point. Okay. So, that is why we are telling that image will be point size, image will be point size or very small size. Okay. Now, object beyond C. So, this is the C center of curvature. So, if it is the object, so we will get the image between C and F. Now, if it is at the center, at the this object is at the center of curvature C, then you will get the image at the same point at C. But so, this is the inverted one, this is the real one. Okay. So, real image is real inverted and size is increasing. So, in this case equal. So, other two I tried to anyway. So, if you other three, if you draw it, so you will see this image will be larger and larger. Okay. One should try it. Okay. So, so if you go for the second component, very important component in the optical lab, that basically spherical lens. Okay. So, before that let me, so that there also this reflect. So, in this case that is a principle of the refraction, principle of the refraction uh, is applicable. So, in this case basically refraction, not reflection, refraction. Okay. So, in case of mirror, so it is a everything follows the laws of reflection. In case of lens, it follows the refraction. So, what is refraction? You know that this is the incident angle and this is the refracted angle. If and refraction only possible at the interface of the two medium, where the that is the interface of different refractive index n1 and n2. Okay. So, angle is theta and theta r, refracted angle. In this case they are refracted. Earlier I told that theta is angle of reflection. So, laws of reflection is basically n1 sin theta I equal to n2 sin theta r. So, these are basically Snell's law, right. So, you are quite familiar. and the incident ray, reflected ray and normal or tangent are on the same plane, right. So, this is the incident, this is the normal and these are refracted. So, they will be on the same plane, okay. The same as the laws of reflection, second law, okay. So, this tangent, as I told, this in case of convex lens and concave lens, it is a curved surface. So, here also, this ray diagram whatever we draw, so refraction, incident rays and then refracted rays. So, in which direction you will get the refracted rays? It follows the laws of reflection. So, here I am trying to give emphasize that in plane surface, the way you follow the laws of refraction. So, for curved surface also the same laws is followed. Only different is that, so you have to consider that the point of the incident ray on the curved surface. So, there you have to draw a tangent and you have to think this tangent is basically uh, the surface like this, okay. Now, if you draw a normal on this tangent, so normal, so that normal is like this, and with respect to this normal, so there will be refraction, okay, and that refraction will follow the uh, uh, Snell's law, okay. So, refracted angle will be such that it will follow this law, Snell's law, okay. So, it is the either convex lens or concave lens for both cases, for both curved surface. So, this whatever the rays, refracted rays we are drawing, so that is basically following the laws of refraction, okay. So, in this case also similar way, I think I have, yes, I think here I have written. So, in this case also, so this is the principal axis, it is principal axis. So, here two curved surface, okay. In case of mirror you have seen one curved surface. So, it has center of curvature C. So, in this case C1, C2, okay. Also focus will be F1, F2. This radius of curvature of both one, it may be same or may not be same, okay. So, but generally we will deal in the laboratory, so having the same curvature, both curve will have the same curvature, radius of curvature, okay. So, it will have two focal length, okay, one is this side, another is the other side. Generally one is called primary focal length, another is called secondary focal length. So, how it is defined? Primary focal length and secondary focal length, not much important. So, it depends on the in which direction light is falling. So, basically uh, primary focal length we tell this f1, okay, when uh, if you put light source, okay, at the focal point, so you will can generate the parallel rays, okay. So, that focal length we tell this primary focal length, and secondary focal length we tell this when parallel rays will fall on this lens and it will meet a refracted rays will pass through a point on the principal axis. So, that is the basically secondary focal length, okay. That way generally we define primary and secondary, but I do not think it is have much importance, okay. So, if curvature are same for both, so then basically focal length OF1. So, focal length here O is optical center, it is the middle, okay. So, all distance are measured from this optical center O, and other case, in case of mirror, all distance are measured from the pole. I did not mention. Okay. So, middle of the, that is a P basically, whatever I showed you P there, this is called pole. So, all distance are measured from that pole, and here all distance are measured from the center of the lens, right. So, uh, so I have drawn the ray diagram for this convex lens and this for concave lens. So, one thing you can see this mirror, in case of mirror, the for concave mirror is the equivalent ray diagram generally is the equivalent of convex lens, and concave mirror, no, that is the concave mirror and this convex lens, and convex mirror and concave lens. So, their ray diagram are more or less similar. Okay. So, now uh, now this purpose of this using this lens or mirror to form an image of an object. Okay. So, characteristics of the mirror or lens, basically it is we express in terms of the radius of curvature or the focal length. Okay. So, now one parameter is focal length f or radius of curvature r. Then second things is that this where I am putting the object. So, that distance we tell this object distance, this generally we express. So, focal length if it is f, this object distance we express by say u, and then where this image is formed. So, distance of this image from the pole in case of mirror or from the optical center of the lens. So, this distance we tell in terms of p, right. So, they are related, So, that relation I will tell you, So, this relation in case of mirror, so 1 by V plus 1 by U equal to 1 by F, right. Okay. And image size are different than the object size. So, this we express as in terms of magnification. So, this magnification M is equal to basically image height divided by object height. It comes equal to minus V by U. Okay. And for lens, this relation is basically 1 by V minus 1 by U equal to 1 by F. Okay. And magnification is height of the image divided by height of the object equal to V by U. Here minus V by U, here plus V by U. Here it is plus 1 by V plus 1 by U, here 1 by V minus 1 by U. Okay. So, this here this difference is basically in sign, relation are similar for magnification as well as this lens and mirror relation are similar. So, basically if you follow the sign convention, then you can tell this if you put the object in left side of the mirror or lens, so image whether it is on the left side or it is on the right side. Also from the sign you can tell this image you are getting, so whether it is inverted one or it is erect one. Okay. So, If we follow the sign convention, so those information we can tell from the sign. So, the sign convention will follow generally Cartesian sign convention, Cartesian coordinate sign convention will follow. So, this is the x axis, this is the y axis, and then this is the z axis. So, forget z axis, x and y, let us concentrate for 2 dimension. Okay. So, if it is the lens or mirror position, okay. So, from distance we will measure from the pole or from the optical center. Okay. So, if this is the object and its height is say h and it is upward direction with respect to the principal axis x axis. So, it is along the y axis, right, positive y axis. So, this if so, so this will take as a positive. If image or this can be image or the object. So, if image or object is this way downward, okay. So, this is the negative y axis. So, this will take as a negative. Okay. Similarly, if the distance of object or image starting from the pole or optical center, if for measuring the distance, if we have to go against the incident direction of the incident ray. So, this is the say direction of the incident ray. So, if we have to measure the distance of an object or image against the incident ray direction, that means in this direction. So, this is basically negative x direction. So, that distance will take as a negative, that distance will take as a negative. If distance of object or image we measure along the incident ray direction, so that means this direction positive x direction, okay. So, then that distance will take as a positive, okay. So, u or v, it will be positive or negative, okay, or the image or object height, okay, it will be positive or negative. So, that we can find out, we will find out following this sign convention. Okay. So, I think these are the information, is just 12th class knowledge one need, and when we will do experiment in the laboratory, this knowledge we require. Okay. We have this knowledge, but we have to implement this knowledge in the laboratory. Only difference is that we know Ohm's law. Okay. Any student will tell Ohm's law, and when we will go to laboratory for verification of the Ohm's law, basically we have to change the current and measure the voltage, see the change of the voltage or vice versa, okay, and then we have to find out that I versus V curve is a straight line, okay. But we know the Ohm's law, but when we go to implement in the laboratory, we find difficulties, okay. As if from my experience what I have seen that, so whatever the definition we have learned, as if it is a separate thing, when we are working in the laboratory, we are dealing with the instrument only, without thinking about the theory whatever we have learned separately in class. So, but it is not like this. whatever we learn, that Ohm's law we know very well, whatever I told you we know very well, okay. But when we will go to lab, so we have to remember whatever we are going to do in the laboratory, there we have to follow this theory, whatever we have learned. And when we are doing experiment, we have to look back to the theory, what we have learned. So if we can combine these two, this theory, whatever we have learned, and if we believe that we are going to implement in the laboratory for doing the experiment, then you can do the experiment easily, you can understand the experiment easily. So that's why I your known things I just repeated. Okay, so I will stop here. Thank you.